All right, so this is going to be a little bit of abstractness going on here. This is for those who really want to know what a real number is. The simple form of a real number is anything of the form integer dot numbers, or maybe I should say digits. Um, okay, so something like 37.58913722. Um, you know, I don't know what that is. You just keep on kind of going, and so you need some kind of formula in order to say that. But um, you need a formula to define it. There's no way to just sort of can't write out all the real numbers. So something like 1.6, and then you got 0, 0, 0. It's all zeros, zeros, right? That's fine. That's a rational number. And rational numbers always have patterns, always a repeating pattern. So if you had a number with a repeating pattern, so like let's say 1.67373373, let's call that x. Then if you shift it over by the kind of period of the pattern, how much, like how long it takes to repeat. Here it repeats for 2 digits, so I'm going to compute 100x equals 167 point, yeah, so move that, and then you get a 3, and then you get 7, 3, 7, 3, right? And so now you subtract these two things, and you get 99x equals 167, sorry, so 167.3 minus 1.6, right? And the rest, this is the trick, they all canceled. And so this was 166. That's this 3, this 6 is more than that, so scratch that. And then that becomes 4, 7, so 165.7, right? Or x equals 990 divided by 1657. Right, so there you are. So that's going if you had a repeating thing to get to a rational. If you have a rational, you just divide the thing, the denominator, into the numerator, and you will eventually get the same remainder at some point, and then the whole process will repeat at that loop. So if you actually did this division, after the first 7, 3, you would end up with the same remainder as you, like after that 3, you get the same remainder that led one to the 7. And at that point, it would just cycle. Okay, good. So in some sense, that is a definition of real numbers, just decimals that go on forever. It's a little bit vague. So here's sort of a precise definition. I happen to like it. It's different than the definition in the other systems, quite frankly. I mean, any of the definitions of real numbers is going to be different because it's quite a different thing. It's filling in gaps. That's the idea. So you have all these rational numbers already, and the real numbers, I mean the irrational numbers, are all in between them, right? So it's like filling that up until it's solid. Rational numbers are very sort of few and far between. I mean, not really. You can get as close as you want between two rational numbers, but it's still lots of gaps. So the real numbers fill that in. And a precise definition of this thing, well, we didn't talk about inequalities. So just sort of before we get to that precise definition, is 3/4 less than or greater than 5/8? Just do this warm up. So 3 is less than 5 because I can map this 3 into these digits, and then I have 2 left over, right? So we do know that 3 is less than 5. And we know that 4 is less than 8. But does that tell us anything about 3/4 versus 5? No, not really. Hopeless. So what we do need to do for comparing rational numbers is same denominators. So convert this to 6/8. And then you have 5/8. And then it's clear that this is greater than, because 6 is greater than 5. You have 6 of the 1/8 kinds, and 5 is the 1/8. So that's nice. So that's the fundamental notion of the inequality between two rational numbers, is same denominators and then compare the tops. But as it happens, you can also cross multiply, same as doing like 3 times 8 versus 5 times 4, which is 24 and 20, and so that's greater than. But it kind of like gets a little weird. So I like to think of the same common denominators, and then you can just wipe them out, right? Okay. So why did I bring up inequalities all of a sudden? Because basically real numbers are sets, containers. Numbers are containers with all the rationals below that real number. Yeah. And it's easiest to just think of it in terms of positive stuff, but include the negatives by going on. But so as an example, the square root of 2 would be the container of rationals x such that x squared is less than 2. Right? So we're able to express the condition in terms of stuff we already have. And so, for example, 3/2 squared is equal to 9/4, which is greater than 2. So not in that set. let's say 3/4 squared, it's 9/16, which is less than 2, so in that set. 5/4 squared is 25/16, which is also less than 2, so it's in that set. Right? And so we already kind of know that the square root of 2 is located between 3/2 and 5/4. And so we kind of narrow the range, and we're defining out what rationals are in the set, and then you get your square root of 2. The square root of 2 is everything below the square root of 2. The real number 3 so real number 3 is all the set x such that x is less than 3. So you get everything going all the way up to 3, as close as you can get, but not actually including 3. And that's what 3 represents. So 3 is like, 3 is the upper bound of that set. All right. So that's basically what a real number is. And all those decimal approximations, so like the square root of 2 is equal to something like 1.41 something. And so 1.44 squared is less than 2. That's in that set, right? And so as you approximate this thing, you can get ever closer, and all those approximations are in that set. And as you get closer and closer, you're closing in on that boundary. And so that's in the sense that, that's how you can kind of get the real numbers. All right, so just like before, we need to define addition and multiplication. So x plus y is defined by adding all the elements in there, in the two sets. That gives you a new set, and that's the real number. So, like if I was doing 2 plus 3 here, then it would be like 1.5 plus 2.75, which is equal to 4.25, so that's in the set. It's in that set. And as I get closer, like 1.9 plus 2.9, well, that's equal to 4.8. And 1.99 plus 2.99 is equal to I guess it's like 4.98, right? And so getting closer and closer to 5, which of course 2 plus 3 equals 5. Right? Multiplication is similar. So 2 times 3 is just like these things. So you could do like 1.9 times 2.9, and that's equal to whatever it is. I don't care. It'll be close to 6, right? That's the point. So we've defined this thing that allows us to talk about things that don't exist with rational numbers, right? We don't actually care about 2 plus 3. What we do care about is like, what does square root of 2 plus square root of 3 mean, right? And because we've got these two sets of rational numbers that represent the square root of 2 and square root of 3, we can actually add them together and you get what that's supposed to be. And, you know, so like, this is kind of like 1.4 and plus 1.7. And so that's kind of like 2.7, 3.1, right? And as you get better and better approximations of square root of 2 and square root of 3, you get better approximations of what their sum is, what their multiplication is, what their division is, and so forth. And there are some things that I'm ignoring here. With the multiplication, for example, you only want to consider the multiplying of the positive stuff, because the negatives times themselves becomes positive big, and that becomes a mess. So, you know, there are things I'm sweeping under the rug. Subtraction, if you want to define subtraction definitively, I should say directly, then essentially you would subtract off things from the stuff outside of the set. But I would probably just go with negation is kind of, well, yeah, so like if you had like x less than 3, so that's 3. 3. Then minus 3 is basically all the x less than minus 3, obviously. But that's also kind of negate the stuff that x is greater than 3. I don't know. So, you know, negatives kind of flipping what's above and below, and so you do that. And then taking the reciprocal of something, 1 over, is 1 overing the stuff in that set. It's larger. Anyway, so there's a lot of like little things to deal with there, but the basic idea is that I'm just saying, here's how I want to think of it. I want to call this thing everything below this condition, and that's the number itself. And then I can have an arithmetic of all that, and it fills up all the gaps, because you can say everything below this bit, so it just magically appears. And it includes all these decimal numbers, because every time you chop off that decimal number, you're in that set, right? You're creeping up on the actual number. You're flushing that out. Okay, so that's how you define the real numbers. We still need to actually say how to compute these numbers.